Have you ever wondered what the code behind our own thinking looks like, or how a computer actually makes a decision? Well, today, we're diving into the fundamental language that powers all of it. We're talking about propositional logic, the basic universal rules of reasoning.
So, let's jump right in and put your intuition to the test. I've got two options for you. Which one of these is a logical proposition? Is it the statement, York University is in Toronto? Or is it the question, do you like this class? Think about it for a second.
If you went with the statement, you nailed it. And here's why. Propositional logic only works with declarative statements. Statements that you can look at and say, yep, that's true, or nope, that's false. A question can't be true or false, right? So it's not a proposition. And that one simple idea is the key to everything we're about to cover.
So here's our game plan. We're going to start with that core concept, true or false. Then, we'll see how to combine simple ideas using some basic building blocks. We'll connect the dots with the power players, and, or, and not. Then we'll put it all to the test with this awesome tool called the truth table. And finally, we'll see how all of this is exactly how computers think.
All right, first up, true or false. Let's get a solid definition for what we could call the single atom of all logic.
So here's the official definition. A proposition is just a statement that is either true or false. And here's the kicker. It can't be both. It's one or the other. So York University is in Toronto is a proposition because, well, it's true. York University is in downtown Toronto is also a proposition because it's definitively false. Both of them work because they have a clear, non-negotiable truth value.
Okay, so now that we have our basic unit, our little logic atom, let's figure out how we can start connecting them together to build bigger, more interesting thoughts. The absolute simplest thing you can do to a proposition is use negation. You can just call it not. It's an operator that does one thing and one thing only. It flips the truth value. It's like a light switch. If a statement is true, not makes it false. If it's false, not makes it true. Simple as that. For example, if our proposition, let's call it P, is Michael's PC runs Linux, then not P is just, it is not the case that Michael's PC runs Linux. Or, more naturally, Michael's PC doesn't run Linux. It's a really straightforward flip.
And this brings us to a really powerful tool called a truth table. All it does is map out every possible outcome. As you can see, the truth table for not is super simple. If P is true, then not P is false. And if P is false, not P is true. We're going to see how these tables help us untangle way more complex ideas in just a minute.
Okay, so we can flip a proposition's value. But the real power, the real fun, starts when we begin connecting two separate propositions together. First up is the conjunction, but you and I know it as and. The rule for and is really, really strict. The combined statement P and Q is only true if P is true and Q is true. If even one of them is false, the whole thing comes crashing down. Both have to be true, no exceptions. And the truth table for and makes this crystal clear. Just look, we have 4 possible combos for P and Q. But notice how only one of them, that very top row where they are both true, gives us a true result. Every other possibility is false. So if and was the strict one, meet its more easygoing cousin, disjunction, or. Unlike and, or is much more inclusive. A statement connected by or is true if at least one of the parts is true. So P can be true, Q can be true, or both can be true. The only way for an or statement to be false is if both parts are false. Now here's what's so cool. If you look at this truth table for or, it's pretty much the mirror image of the and table, isn't it? 3 out of the 4 outcomes are true. The only time P or Q is false is that very last row where P is false and Q is false. So we have our basic building blocks, not, and or. Now let's put them together to build one of the most common and most powerful logical structures there is, the good old if-then statement. This is a conditional statement or an implication. We read P arrow Q as if P, then Q. Now P is our hypothesis and Q is our conclusion. And there is only one very specific situation where this whole statement is considered false, when the first part is true, but the second part is false. Think of it like a broken promise. If I say, if you work hard, you'll be a topper, the only way I've lied to you is if you do work hard, but you don't become a topper. Now, a conditional statement has some important relatives. If our original statement is, if you work hard, you are a topper. The converse flips it around. If you are a topper, you work hard. That's not necessarily true, is it? Same with the inverse, but check out the contrapositive. If you are not a topper, then you don't work hard. That statement is logically identical to the original one. They're either both true or both false, which is a super useful trick in arguments and proofs.
So, how do we prove that its statement and its contrapositive are actually the same? You guessed it, a truth table. And when statements get really messy, we can still figure them out with these simple steps. You just make a column for each basic piece, then build it up one operation at a time, until you get your final answer. It's a method that works every single time.
Let's just take a quick peek at a more complex table in action. We'll just trace one row together, okay? Let's do the second row. Here, P is true, Q is false, and R is true. First, the small parts. Not Q must be true because Q is false. Not R must be false. Next, we do P and not Q. Well, that's true and true, so the result is true. Finally, we take that result, true, and we OR it with not R, which was false. True or false gives us a final answer of true. See? No matter how complicated it looks, this step-by-step process always gets you the right answer. Okay, that was a lot of theory, but so what? Why does any of this actually matter in the real world? Well, it turns out this isn't just some abstract exercise. This is the literal language that the entire digital universe is built on. Here it is. This is the magic connection. The simple binary choice of true and false that we've been using is exactly the same as the ones and zeros that form the basis of all computing. True is 1. False is 0. That's the secret. And this means that every single logical tool we just talked about has a direct counterpart in your computer. Not just flips a bit from a 1 to a 0, and checks if 2 bits are both 1. You know, when you search for cheap and good restaurants, you're literally using a logical conjunction. The tiny little logic gates etched into a computer chip are just physical versions of these exact same rules. So when a programmer writes a piece of code with an if-then statement, like if you have the flu, then you miss the final exam, what they are really doing is building that same conditional proposition we just mapped out. This is how software makes every single decision, from a simple app to the most complex AI. And that brings us to the end. So now that you know the fundamental rules of logic, here's a final thought to leave you with. What's a really complex decision in your own life that you could, if you tried, break down into a series of simple, connected, true or false statements? Turns out the code behind our thinking is something we can all learn to read. Thanks for watching.